This is the 2024 Higher Level Applied Maths Leaving Cert paper question 4. A snowboarder of mass m is travelling with velocity v1 when he enters a circular arc AB at point A. So he's entering here and he's going to come up along this way. AB has radius 6.7 meters and center C. AB and C lie in a vertical plane. AC is vertical, so this is vertical, and BC here is horizontal. A student models the motion of the snowboarder ignoring the effects of friction and air resistance. Draw a diagram to show the forces acting on the snowboarder when he is at a point D, where CD makes an angle alpha to the downward vertical. Okay, so let's do that. So we're going to take the snowboarder, let's say here, this is at the point D. We're going to put in the weight first anyway, so that's down along here. We're going to say M is the mass of the snowboarder, and I'm going to put in the reaction as well. That's the reaction force. So the weight here is going to be mg. I'll actually resolve it as well, and the reaction force is going to be in this way towards the center. This is going to be R in along here. So you can imagine the arc is coming around this way, and if we resolve it down this way and this way, and call this angle here alpha, let's say this is mg cos alpha, and here we have mg sine alpha. Now there's also a centripetal force here which will come in along this way as well. I'll just put in centripetal force, which is just mv squared over r. Not sure if you have to include that, but we'll just include it there anyway. Okay, so that's really it for part 1. Let's have a look at part 2. Express the reaction force on the snowboarder at point D in terms of mv1 and alpha. So what I'll do is I'll just copy down the diagram again. We'll need that. So let's start with the energy equations. So the energy equation first of all has an mg h0. This is the potential energy at point A. So h0 we'll say is the height at point A, plus the kinetic energy at point A, which is a half mv1 squared. Remember, v1 is the velocity at A. This is equal to mg, again the potential energy, mgh. We've got to work out the height, I'll do that in a second, plus half mv squared. Now this v here is the velocity at D, so we're just calling it v. So let's work out this height here. Now we want to work out the height, this height here, the height down along here. So really what we've got to do is work out this distance here. So I'm going to work out this distance first, so that's just 6.7 cos alpha, because we have an alpha here and this is 6.7 out here. The hypotenuse out along here is 6.7 sine alpha, we don't need that, but this here is 6.7 cos alpha. So to find this distance here, we just take 6.7 and subtract 6.7 cos alpha. So that's the height at D. So it is 6.7 minus 6.7 cos alpha. So let's just simplify all of this. The height at A is 0, so this whole thing just becomes 0. So we've got a half mv1 squared is equal to, I'm going to multiply this out, 6.7 mg minus 6.7 mg cos alpha plus a half mv squared. Okay, so next thing I'm going to do is just multiply across by 2 and do a bit of factorizing. So it's mv1 squared is equal to, I've got to multiply these 6.7s by 2 to give me 13.4, and I'm also going to factorize out the mg, so that'll leave me with 1 minus cos alpha, and then out here multiply by 2 will leave me with mv squared. The next thing I'm going to do is look at the centripetal force, which is mv squared over r, which is equal to the reaction force minus mg cos alpha. So remember, the reaction force is working in along this way, the force opposing it is out along this way, and we resolved that in part 1 and we found that was mg cos alpha. So that's where this comes from here. By the way, I'll call this equation 1, this equation 2 here. So what I'm going to do next here is just multiply across by r. R, remember, is the radius of the circle, so it's mv squared is equal to 6.7 times r minus mg cos alpha. So now I have two equations, and I'm just going to do a little bit of substitution here. Remember, we don't want v, we don't want these v's here. So I'm going to substitute, this is mv squared here, I'm going to substitute that in here. That'll give me an equation without the v, and hopefully we'll be able to get where we want to go from there. So let's look at our two equations and do a bit of substitution. So I'm going to take equation 1, which is mv1 squared, which is equal to 13.4 mg 1 minus cos alpha plus, now the mv squared, I'm just going to put this in instead of it, so it's 6.7, or minus mg cos alpha. Okay, so what I'm going to do next is I'm going to multiply this out here, and I'm going to bring it over to the left hand side. So that will give me, let's see, mv1 squared minus 13.4 mg plus 13.4 mg cos alpha, and that's equal to 6.7 or minus 6.7 mg cos alpha. Okay, next line. So I'm just going to get the or on its own. So it's mv1 squared minus 13.4 mg plus 13.4 mg cos alpha minus it's plus 6.7 mg cos alpha. That'll leave me with this bit here, so now I've just got to divide by 6.7. So let's do that. That's 6.7, and that gives me the or, which is what we were asked to do. However, I will just simplify it a little bit. We can add these two anyway. So let's do that. We get mv1 squared minus 13.4 mg. When you add those two, you get 20.1 mg cos alpha. That's all over 6.7, and that's equal to or. So that's really it. But what I might do here is just give you the other version where you multiply out the g's. So that's mv12 minus 131.32 m plus 196.98 m cos alpha, and that's all over 6.7, and that's or. So that's part A2 finished. So the snowboarder reaches point B with vertical velocity v2. Express v2 in terms of v1. So let's write out the energy equation. We've got mgh0 at point A, the height is 0, plus half mv1 squared. Remember, v1 was the velocity at A. That's equal to, again, mg. This time the height is 6.7, because remember he's at B at this stage, and B is horizontal with C, and C is vertically above A. So this distance here is 6.7. And the kinetic energy then is half mv2 squared. So I think we have everything we need here. We don't have to do any kind of substitution into the centripetal force equation or anything like that. So what I'm going to do is, let's see, well, this will disappear because h0 is 0. I'm going to divide across by m, and I'm going to multiply by 2 to get rid of those halves. So that'll leave me with v1 squared is equal to 13.4 g plus v2 squared. We want to get v2 on its own, so that's v1 squared minus 13.4 g is equal to v2 squared. All we've got to do now is square root both sides, and that should give us our answer, I think. So v1 squared minus 13.4 g. Now again here, you know, you can multiply out the g. Not sure if they require that, but so that's v1 squared minus 131.32. Okay, and that's it for part 3. At point B, the snowboarder leaves the arc and moves vertically upwards through the air. The student wishes to calculate v, the velocity of the snowboarder, t seconds after he leaves the arc. The force due to air resistance is now modeled by mkV. Draw a diagram to show the forces acting on the snowboarder while he is moving upwards through the air. Okay, so if we take the snowboarder as being, let's say, a dot here, we have his weight anyway, which is acting down. So his weight, which is, let's say, mg. And we also have air resistance, which is going to be acting downwards as well. So the air resistance which is given by mkV. And this is our snowboarder here. Okay, that's really it for this part of the question. So this is part V. Show that while the snowboarder is moving upwards through the air, the rate of change of V with respect to t can be expressed by the differential equation dv dt is equal to minus g plus kv. Okay, so in the previous section we were asked to do a force diagram, so that should give you a kind of a hint as to where we need to go in this section. So we're going to start with forces mass times acceleration. The forces were minus mkv minus mg, and that's equal to mass times acceleration. So they're minus because we're taking up as being positive. So let's divide across by m. So that'll give us minus kv minus g is equal to a. Now a is just dv dt. So minus kv minus g is just dv dt, is the rate of change of velocity with respect to time. So we've just got to finally just take that minus out. So it's dv dt is equal to minus, we put the g first because that's the way they have it in the question, and then it's plus kv. And that's it. That's all we had to do. Solve the differential equation to find an expression for v in terms of t, k, and v1. Okay, so we're going to start with dv dt is equal to minus g plus kv. We'll just separate these out. So you got dv is equal to minus g plus kv dt. And we're going to divide across by g plus kv dv is equal to minus dt. So what we're going to do here is we're going to integrate both sides of this equation, and the variables then that I'm going to put in, or the limits I should say, are going to be v2 here, because remember that's his initial velocity just as he leaves B, and we want to find v, and on the other side the initial time is going to be 0 for some time t. Okay, so when you integrate 1 over g plus kv, you're going to get, well, 1 over something is going to be log of the something, so it's going to be log g plus kv anyway. But if you just check this out, if you differentiate this, do you get this here? But if you differentiate this, you get 1 over g plus kv, but then you've got to differentiate this here by the chain rule, so you end up with an extra k, so you want to get rid of that, so it's going to be 1 over k on this side. On this side here, it is going to be just minus t, and our limits then are v2 and v, and 0 and t. Okay, so let's work all this out. So we just want to substitute in the v's first of all, so it's 1 over k log g plus kv, and then we've got to subtract 1 over k log g plus kv2. On this side here I've got a minus t, and then if I substitute in 0 I'll just get 0. So that's my equation. First thing I'm going to do is just factorize out this 1 over k. That'll leave me with log. By the way, what I'll do as well is I'll end up with these two logs here, so by the laws of logs I'm just going to divide these two. And that's equal to minus t. So let's just multiply across by k. So that'll leave me with log of g plus kv over g plus kv2 is equal to minus kt. So I have it in log form. I'm going to convert it to index form. So it's e to the power, remember there's an e here if you like, this is natural log kt is equal to g plus kv over g plus kv2. Now what we want to do here is try and get v on its own. So what I'm going to do next is multiply across by g plus kv2. So it's e to the power minus kt times g plus kv2 is equal to g plus kv. The next thing I'm going to do is subtract the g and divide by the k. So it's e to the power minus kt g plus kv2 minus g. Then I'm going to divide by k, and that gives me v. So the next thing we've got to do is look at the fact that in an earlier question, part 3, we found that v2 is equal to the square root of v1 squared minus 13.4g. So we don't want v2 in our answer, we need to get rid of that, so we're going to substitute this in instead. So finally we get v is equal to e to the power minus kt g plus k times the square root of v1 squared minus 13.4g, and then minus g out here, and all divided by k. Or again, we can say v is equal to e to the power minus kt 9.8 plus k times the square root of v1 squared minus 131.32 minus 9.8 all over k. Okay, so that's it for this question.